and welcome to the last and shortest video in the series, Astronomical Spectroscopy. How we know what we know. I'm Dewey Anderson. This is a 5-part series intended to explain how astronomers use spectroscopy to learn about stars, planets, galaxies, and the universe. The first video covered some background physics stuff about light and heat that you need in order to understand spectroscopy. The second video discussed continuum radiation and what's called the black body spectrum. We saw how that can be used to determine the temperature, luminosity, and ultimately the distance to stars. The third video talked about spectral lines that come from discrete transitions and how they can be used to determine what stars are made of. The fourth video covered the Doppler effect, the shift in energy of photons due to the motion of the source. There was a bunch of different things we learned from measuring that. This last video talks about the splitting of spectral lines due to magnetic fields. This is called the Zeeman effect, and it means that we can actually measure the strength of magnetic fields in, say, the surface of the sun. Now, one last time, I'll start with a quick reminder, some of the background physics stuff from part 1, just so that it's fresh in your mind. We view light as a stream of light particles called photons. They have energy measured in electron volts, or EVs for short. Photons can be created when there are changes in electrically charged systems, like electrons changing orbits in atoms. The rules of quantum mechanics say that only certain electron orbits are allowed in atoms. That means that when they change orbits, there's only a certain set of energy changes allowed, and that means that the photons that are emitted can only have energies from that discrete set. We say that those are discrete transitions. When that light is passed through a slit into a spectrometer, the photons are spread out based on energy, forming a set of lines at the energies for the emitted photons. Now, this is what an image of the emission lines coming from a hot hydrogen gas might look like. When we plot the spectrum as a graph, these spectral lines result in spikes in the graph if the electron is dropping down in energy, emitting a photon. We call these spectral emission lines. But it can also happen that photons of just the right energy knock electrons up to a higher orbit. Those photons don't make it to our detector. This results in dips in the graph of the spectrum. We call these spectral absorption lines. In actual practice, astronomers are usually measuring absorption lines. Now, on to our last topic, the Zeeman effect and how it can be used to measure magnetic fields, and how that showed us that sunspots are magnetic regions in the sun's atmosphere. Now, first, a word about magnetic fields. You may have seen something like this before, maybe just a picture or maybe in a grade school science class. It's a typical bar magnet with a north end and a south end. Iron filings are sprinkled around it and they form a pattern showing the magnetic field lines. Now, what's not apparent in the iron filings is that magnetic field lines are actually directed lines. It's our convention to draw them as going from the north pole of the magnet towards the south pole. Now, this makes it clear that north and south poles are different. If you bring two magnets near each other and you have the north pole of one near the south pole of the other, you can see how the field lines go from the left magnet's north pole towards the right magnet's south pole. But if you position them so that their north poles are together, you can see that the field lines diverge away from between the two magnets. You can almost see the field lines wanting to push the magnets apart. Now, one thing to make clear here, we draw the field lines as separate lines. That might lead you to think that there's no magnetic field between the lines. Well, that's not the case. The field is everywhere, and we're just drawing some lines to show the shape and direction. It'd be a little like drawing flow lines on a picture of a river to show which way it flows. Water is definitely flowing between the lines. And now I want to say something about how physicists think of magnetic fields. They're less concerned with the fact that magnets attract each other or repel each other or stick to some metals. The important thing to a physicist is how they affect the path of a moving electron. It's a rather odd effect. Imagine you have a magnet positioned far behind the screen, and it's oriented so that its north pole is toward you and the south pole is away. And in that case, the magnetic field lines will be coming out of the screen toward you. This is a side view of that situation. If the magnet is far enough behind the screen, then the field lines at the screen will be almost parallel and perpendicular to the screen. So you will be seeing those field lines end on. Now let's flip around to your view of the situation. You see a blank screen with magnetic field lines coming almost straight out at you. To show that, I've drawn little dots to represent the lines viewed end on. Now imagine there is no magnetic field and you have an electron moving across from left to right. I would draw that like this. Now do that again, but with the magnetic field coming out of the screen at you. That would look like this. The magnetic field would cause the electron's path to curve. That's what magnetic fields do. They change the path of moving electrons. In this case, it makes the electron turn to its left. And if I continued the drawing farther, it would have kept turning left and ultimately going in a circle. And if the field lines had been going into the screen instead of out of it, the electron would have turned the other way, turning right. So with that background of what magnetic fields do to the path of moving electrons, let's go back to our basic hydrogen atom with one electron going around it. In those earlier drawings, I didn't usually specify whether it was going around clockwise or counterclockwise. I did mention the spin in the last video, but now I'm talking about the orbital motion. In those cases, the orbital motion of the electron was due to the attractive force of the proton. That makes the electron go around. And if that's all there was, then it wouldn't really matter which way the electron goes. But if magnetic fields can also cause an electron's path to curve, then that will have some effect. Now, as it happens, the magnetic field is a lot weaker than the force due to the proton, so the effect is just a slight change in the energy of the orbits. If, as shown here, the direction of the magnetic field lines is perpendicular to these orbits, coming out of the screen at us, then that will raise the energy of the electron in the atom on the right, and decrease the energy of the one on the left, by just a little bit. You can kind of think of it this way. When there's no magnetic field, it's just the electric force from the proton that makes the electron curve in a path that goes around that proton. For the guy on the right, that's turning left. Same force in the atom on the left makes that electron turn to the right. But remember, the magnetic field will also make the electron turn left. So for our two atoms, for the one on the right, there's now more force on the electron, causing it to turn. I add a little red arrow to show that additional force. So in order to stay in the same orbit, like quantum mechanics says it has to, the electron needs to go a little faster. So that means it has more energy. The opposite is true for the atom on the left. The proton is making it turn right, but the magnetic field wants to make it turn left. So I'll add a little red arrow pointing left. Notice that's opposite to the yellow arrow from the proton force. The proton force is much stronger, and so the result is simply a slightly weaker force making it turn. In order to stay in that orbit, the electron needs to move slower, so that means less energy. How much energy is determined by the strength of the magnetic field. And this will change the energy differences between orbits above and below this one. Just a little. So, for example, the left atom will need to absorb a slightly higher energy photon to get up to a higher orbit, while the higher energy electron on the right will be able to make that jump with a slightly lower energy photon. Now I'm skipping over some quantum mechanical weirdness that makes it a little more complicated than that, but the gist is the same. Electron jumps from, say, orbit number 2 to orbit number 3 will now involve two different energies, and they will show up as two absorption lines very close together in the spectrum. This effect is called Zeeman splitting. And you guessed it, there's an equation for the energy shifts. In this equation, B is the strength of the magnetic field, so it determines how big the energy shift is. The result in the spectrum plot looks a little like the splitting of a spectroscopic binary pair, except they don't move around over the course of the year. By measuring how big the energy difference is, we can invert that equation and compute how strong the magnetic field is. A convenient detail in this is that the different lines will have different polarizations. That is, the photons that are emitted or absorbed in one line will be polarized oppositely to that of the other line. Now, never mind what polarization is. You can think of it as photons spinning along the direction of motion. In some cases it's clockwise, in others it's counterclockwise. And that means that we can tell not only the strength of the field, but whether the magnetic field lines are coming toward us or away from us. That is, we can tell the difference between looking at the north end or the south end of the magnet. Sometimes the splitting of the two lines is so slight that it just looks like line broadening, something I talked about in the previous video. Now here I show the counterclockwise line in red and the slightly higher energy clockwise line in green. Now I'm just using the colors to make them easy to see. Nothing here is actually red or green. The white outline shows the sum of the two lines. That is, what you'd actually get on your spectrometer plot. It looks like a single fat line. But by using polarizing filters, it's possible to block out one and just see the other. Go back and forth, and you can detect whether there are actually two overlapping lines or not. In addition to measuring the overall strength of the magnetic fields of a star, this can also be done scanning across the surface of the sun, building up magnetic field information as you go, mapping the magnetic field on the sun. Such a map is called a magnetogram. This picture shows a regular visible light image of the sun on the left, taken when it had a lot of sunspots, and the corresponding magnetogram on the right showing the strong magnetic fields around sunspots. This is how they figured out that sunspots are due to the magnetic fields on the sun. The black and white areas of the magnetogram indicate different polarities, that is, magnetic field lines coming toward us or away from us. If the magnetic field is not coming straight at us, then there will also be some photons that are not shifted, and they will appear in the middle at the expected energy. By comparing the strengths of the shifted absorption lines with the unshifted lines, it's actually possible to determine intermediate directions of the magnetic field lines. So it's not just purely north or south. Now, it turns out that a strong magnetic field inhibits the convective motion of the sun's atmosphere, making it harder for hot stuff to come up from below. That means that the plasma on the surface that has been radiating away its heat can't be replaced by new hot stuff coming up from below as easily. That makes the material in the area of a strong magnetic field cooler than the surrounding photosphere. And cooler stuff looks darker. Remember those Planck blackbody curves? That is why sunspots are dark. Now, in addition, we find that sunspots are often seen in pairs, and we're able to detect that one spot has one magnetic polarity and the other is the opposite. The field lines above the sun go from one spot to the other. Field lines pointing up at one spot, pointing down at the other. The Zeeman effect lets us see that difference. And at times, in photographs, we can actually see plasma trapped in those field lines arcing above the solar surface as prominences. Now, the sun goes through a cycle over a period of about 11 years, where the number of sunspots increases and then decreases. During a period of many sunspots, a so-called solar maximum, the sunspot pairs tend to be near the same latitude, with one spot leading the other as the sun rotates. Kind of like a sunspot parade moving left to right across the face of the sun. At one solar maximum, it might be noticed that the leading spot has a north magnetic polarity. Then, over 11 years or so, the number of sunspots will drop to 0 and then increase again. But this time it will be noticed that the leading sunspot has a south magnetic polarity. In this magnetogram, which uses blue and yellow to indicate magnetic north and south polarity, the spots in the northern hemisphere in 1989 were being led by blue polarity, whichever one that was. And in 2000, they were being led by yellow polarity. So what astronomers originally thought was an 11-year cycle is actually a 22-year cycle. One solar max with one polarity, then one solar max with the opposite polarity. And you might also notice that who's leading the parade in the northern hemisphere is the opposite of who's leading the parade in the southern hemisphere. This all helped solar physicists work out what must be happening with the magnetic field lines inside the Sun over the course of this cycle. The Sun has differential rotation near the surface, which means that the plasma near the equator and at the poles are rotating at different rates. The plasma near the equator is actually rotating faster. And it's not just that its linear speed is faster because it's farther from the axis. Its rotation rate is faster. It takes less time to go around once than the stuff near the poles. How do we know that? We got the velocity at different places on the Sun from the Doppler shift, video number 4. This differential rotation results in a shearing effect in the solar atmosphere that drags the magnetic field lines. Over time, they get stretched out latitudinally, sideways. You can see that beginning to happen in the middle drawing. At solar maximum, when that stretching is the strongest, the third drawing, the field breaks through the surface, making sunspot pairs with opposite polarity. Then this whole thing breaks down, the overall field of the Sun reverses, and we do the dance again. We can work this stuff out because we can measure the magnetic fields because of the Zeeman effect. Spectroscopy. So, what have we got? Magnetic fields affect the energy levels of electron orbits, and those changes can be detected in the spectrum to measure the strength and direction of the fields. That's how we figured out sunspots are magnetic. So, that does it. By measuring the energies of photons coming from stars, planets, interstellar gas, galaxies, we can figure out how hot they are, how far away they are, what they're made of, how fast they're moving, and how strong magnetic fields are. That's a lot of information to get from one kind of measurement: spectroscopy. Thanks for watching.